Hello guys, welcome back to my channel. In this video, we'll be looking at a typical example of a sequence question. So here we go. Determine the formula for the nth term of the following sequences. Now, when we say the formula for the nth term, what it means is that when I generate a formula for this particular sequence, when I put in 1, I should get the first term. When I put in 2, I should get the second term, and so on. So let's look at the first sequence, sequence A. My first sequence, the terms are 3, 7, 11, 15. Now, clearly, I can see that I am going up by 4, which makes this an arithmetic sequence. If I go 3 plus 4, I get 7, 7 plus 4, I get 11. So I know that this is arithmetic. Now, let us recall the formula for an arithmetic sequence. We know that an is equal to a plus n minus 1 times d. Now bear in mind that a is my first term and d is my common difference. So here I'm going to have an, my first term is 3. I'm going to have n minus 1 times my common difference, which is 4. And all I really need to do here is tidy up the sequence. So I'm going to have an equal 3 plus 4n minus 4, which we can just say that an equal 4n minus 1. And this would be the formula for my sequence. Now let us see if it works. Let us see if we can generate the fourth term. If I were to generate the fourth term, it means I would replace n by 4. So if we go 4, so I would have a4 equal 4 times 4 minus 1, which is 16 minus 1, which is 15. So we indeed get the fourth term, which is actually 15. My second sequence here, sequence B, is 2, 6, 18, 54. Now, clearly what I'm doing here is that I'm multiplying each term by 3. Because if I multiply 2 by 3, I get 6. If I multiply 6 by 3, I get 18. And if I multiply 18 by 3, I get 54. So this tells me that this sequence is geometric. Now let us recall the formula for a geometric sequence. It says that an is equal to ar to the n minus 1. Now bear in mind that we said that a is the first term and r is a common ratio, or the number I'm multiplying by. So in this case, I'm going to have an equal, my first term is 2, and my common ratio is 3. So that's 2 times 3 to the n minus 1. And this, of course, can't be broken down any further. Now, once again, we could actually test the sequence to see if it is correct. So let us say, for instance, let us test the third term this time. My third term here is 18. So it means that when I put 3 in there, I should get 18. So I'm going to have 2 times 3 to the 3 minus 1, which is going to give me 2 times 3 squared. 3 squared is 9. 2 times 9 is actually equal to 18. So this is indeed correct. In sequence C, we have 15, 3, 9, and 6. Now, in this particular scenario, what it appears that I'm doing is that I'm subtracting 3, because 15 minus 3 is 12, 12 minus 3 is 9, and 9 minus 3 is 6. It is still geometric, so my common difference here is actually negative 3. So let us start by writing down the formula. an is equal to a plus n minus 1 times d. Here my first term is 15 plus n minus 1, and here my common difference is negative 3. But I can't just put minus 3 here because it's going to appear as if I'm subtracting 3. So probably I could put times negative 3. So this is now going to give me 15 minus 3n when I distribute the bracket plus 3. Alright, looking for the like terms, I can say this is negative 3n plus 18, or I could go 18 minus 3n. In both scenarios work, it doesn't really matter. In example D, I have 192, 96, 48, and 24. So in each case, what I'm really doing is half in the term, which actually means I'm multiplying by a half. Okay, let us see what happens in this case. So once I'm multiplying by a common ratio, it makes a sequence geometric. So we can start by writing down the geometric formula. And it says that an is equal to ar to the n minus 1. In this case, my first term a is 192. I'm multiplying by a half in each case, so I'm going to have a half to the n minus 1. And if you want, you can go right ahead. Just put in a random term to see if you can actually test if this is correct, right? So if I want a third term, I could just plug in 3. When I simplify this, I should actually get 48. In sequence E, we have 1/3 as my first term, 2/4 as my second term, 3/5, and then 4/6. Now, it is interesting to see what happens in this sequence because what we can actually do is to isolate the numerator and the denominator. Look at my numerator. I have 1, 2, 3, 4. That in itself is an arithmetic sequence where I'm going up by 1. In my denominator, I have 3, 4, 5, 6. Once again, that is an arithmetic sequence where I'm also going up by 1. So what I can do is to generate a formula for my numerator and to generate a formula for my denominator. Now, we don't always have to go to the formula because by just looking at this 1, 2, 3, the numerator actually represents the position of a term. So the numerator is actually n. So when we go an, my numerator is simply n. All over, looking at my denominator, I'm still going up by 1. My first term is 3. So we could think of this as being n plus 2. Alright, it's 2 more than what the actual position of the term is. So this is n over n plus 2. Note briefly that if you were to apply the formula, you will still get the same thing. But once the sequences are obvious and straightforward, you don't always have to employ the use of the formula. We can simply just write down the sequence, unless we're asked to work it out or show working.